So, I guess the organizers must have been very impressed with my pleasing voice and put me as the last speaker of the day, so that those of you who aren't yet asleep will definitely be asleep by the end of this seminar. But anyway, I'm very happy to be here. IIT Kanpur has always been an invigorating, provided an invigorating atmosphere for me, and unfortunately, several of you have heard this talk before. So, not all of it though. I apologize, but there is something at the end that is different. If you're awake, please listen to that part. So, I'm going to be talking to you about granular flows. So essentially, these are grains like sand, wheat grain, food grains, glass beads, anything in the form of grains that are macroscopic and interact with each other, and yet they are connected to fluids. And the particular problem that I am interested in, that is widely used in the domain of fluid mechanics, is that there is Taylor-Couette flow. That is, you have two concentric cylinders. You have an inner cylinder which you can't see in there, perhaps you can, and then you have an outer transparent cylinder. There is a fluid in between, and when you rotate the inner cylinder, you can measure the viscosity from the torque, and that is why this is very frequently used. In fact, it is the most commonly used viscometric device to measure the viscosity of fluids. But the interesting thing it does is, and this is an old problem, as you increase the rotation rate of the inner cylinder, there is a spontaneous instability, and you start seeing bands of this kind. Okay, this was observed a long time ago and explained by G.I. Taylor using his linear stability analysis, and in fact is one of the great successes of linear stability analysis, because the linear stability gives you the exact transition number, the Taylor number at which the transition takes place. So, and as you go to higher and higher speeds, you get all kinds of secondary transitions. Now, how is this connected with granular materials? So, what I am going to do instead of putting a fluid in between is to put granular material. And well, I wasn't the first to do that, to think of this. I'll come to why this is a sensible thing to do in a slide, but there have been at least two other studies that have used a Couette device to study what kind of measurements one can make if you have a granular material in there. The first actually is not even given here, was Bagnold. He took wax spheres, wax because they are roughly the same density as water, dispersed them in water, and spun the inner cylinder at a very high speed, and discovered what is today known as the Bagnold regime, the regime where the fluid no longer plays a role in the dynamics of the particles, and the particle collisions essentially give you stresses, generate the stress that is transmitted from one wall to the other. Okay, but that is at very high speeds. Now, these studies are at relatively much lower speeds, and these people try to do exactly what I set out to do, and that is to try to measure the equivalent of the viscosity for a column of grains. Okay, in other words, to measure the rheology of a column of grains. Now, these people, this set of investigators found that if you have two kinds of grains mixed together, then you get a spontaneous separation, and you get the same kind of vortices that you get in Taylor-Couette flow of a Newtonian fluid, but the lighter bands over here are of the smaller grains, and the darker bands are of the larger grains. So this is essentially driven by size separation, whereas the instability you see in a column of a Newtonian fluid or even a non-Newtonian fluid has nothing to do with size separation. Now, so what's the connection between grains and fluids? Well, you know, grains do behave like fluids. You could very well imagine doing, dropping fluid through a spout, and it would look roughly the same. Of course, it wouldn't form a heap, but that's the difference between grains and a fluid. And you know, in a continuum sense, one could treat flowing granular material as a strange kind of fluid. The difference is, as I said, grains form a heap. In other words, they can withstand shear stresses without deforming. So they are in between a fluid and a solid, so they have properties of both. And here's an example where you can see both the features in simultaneously happening together. So you have in this channel in which black glass beads are overlaid onto white glass beads, and when you open the gate at the bottom of the channel, you see that there's this region which is absolutely static. There's no deformation there. So you have a solid-like region right next to a flowing liquid-like region. Okay, so one has to take account of both these features when you try to understand the deformation of granular materials. Now, so traditionally, the way people have measured properties of grains of granular materials are using these kinds of devices. So the Jennecke tester essentially creates a rupture surface. Okay, so there are two rings over here. The top ring is placed over the bottom ring, and the gap is completely filled with say sand, and then the top ring is pushed, and you create a rupture surface, and you measure the angular friction, the Coulomb friction that's required to rupture the surface. Okay, essentially for plastic yield. And these are the more sophisticated device where you have a square cavity filled with a granular material whose shape you change because the edges are hinged. And so as you form a parallelogram from a square, you measure the shear stress required for a given normal stress, and you get the plastic properties of this material. And yet another is this triaxial tester, where you apply an axial load and a radial load, and measure the load at which vary those loads until you get the so-called yield surface. And all of these are essentially used to determine the limit of yield. Okay, unlike in fluids, they are not trying to relate the stress to the plastic deformation or plastic deformation rate. They are trying to determine at what point the material yields, and that's, I guess, the most important thing. If you are a civil engineer, you want to know when this building is about to yield so that we can all leave. You're not interested in the building flowing out. Whereas if you are in a process industry, flow is important. Okay, even though you have a material that has a certain yield stress, it does flow beyond the yield stress, and a lot of people are interested in the flowing regime. And for the flow regime, these are not so useful testers, and that's why a cylindrical Couette cell. Now, the cylindrical Couette cell falls in this class of geometries which all produce a viscometric flow. Okay, which means the flows they generate are very easy to analyze, and you can directly relate the stress you measured to properties of models that you have proposed. Okay, so and there's standard geometries that you get in rheometers that you can buy off the shelf. So what would be the stress for say Newtonian fluid or any fluid, doesn't matter whether it's Newtonian or not? Well, all the normal stresses would be equal, and there would be no shear stress at the wall. I mean the vertical shear stress at the wall would be 0. You would of course have an azimuthal shear stress, okay, because you're rotating the inner cylinder, but the vertical shear stress at the wall would be 0. And all the normal stresses would be equal. And most importantly, the stresses are independent of position except the pressure. Okay, so that's why if you measure just the torque, that's enough to give you the viscosity. You don't need to make measurements as a function of the depth of this Couette cell, which is not the case for a granular material. Okay, as I will show you now. So essentially, you can people have divided the mechanics of granular materials in two distinct regimes. This is the gas-like regime, where particles transmit momentum by colliding with each other. The collisions are very short compared to the time of flight, and this very dense regime, where the collisions are relatively long compared to the time of flight between grains. And like in fluid mechanics, you can write down a number that measures the relative importance of these momentum due to collisions, short-term collisions, and momentum transmitted, or the total stress. Okay, this is the numerator is the momentum transmitted per unit area per unit time, momentum flux by collisions, and the denominator just the total stress. Gamma dot here is the shear rate. Okay, now this Savage number was first proposed by Stuart Savage as a measure of what regime you're in, and the more recent use of this inertia number is essentially simply just a square root of the Savage number. And the observations tell you that if the Savage number is below 10 to the minus 6, you are in this regime. And in this regime, the stress does not depend on the rate of deformation. Okay, so if you double the speed of this inner cylinder, the stress would remain unchanged. Just like you have a block going down a slope, the force the block exerts on the slope does not depend on its speed at low enough speeds. Okay, so what does all this have to do with rheometry? So suppose you have just a static column, so you have grains in a column. Unlike in a fluid, the column will exert traction on this wall and vice versa, and the traction exerted by the wall on the column, essentially friction, if you carry out a very simple calculation, friction exerted by the wall on the column, even when it's not moving, tells you that the stresses saturate within a short distance. So this is the dimensionless distance from the top, and these are the dimensionless stresses. Okay, the stresses saturate very quickly, exponentially in fact, from the top, and that's simply because the weight is transmitted, or the weight of this area beyond a certain point is fully held by the walls. Okay, unlike in a fluid where the weight is just transmitted below, and that's why the pressure keeps going up linearly with distance. So now, what would you get if you now sheared this column, as in this case? The classical plasticity theories that are used for granular materials have this general form if you write them in the stress explicit form. They are not generally written in a stress explicit form, but you can write them in this manner. Okay, so most generally you have a stress, you have an isotropic part of the stress, you have a part that's linear in the deformation rate. So d prime here is the rate of deformation minus the isotropic part. Okay, so it's the deviator of the deformation rate, and you have a quadratic part in general. Okay, for simple theories, the quadratic part goes away. But the interesting thing is, if you apply this to this simple flow, the viscometric flow, then what it predicts is, so in the viscometric flow, I assume that the velocity is purely azimuthal. Okay, the cylinder simply rotates the material around and round in circles inside the cylinder, inside the column. The radial and vertical velocities are 0. Then you get the prediction that the stresses are constant. I'm sorry, they're not all equal, but they're related to each other through this constant k. Okay, and this vertical shear stress is 0. So unlike in a static column where the vertical stress is not 0 and the column holds up the weight of the material, here all these theories suggest that there should be no vertical stress the moment you start shearing the column. So is that indeed the case? I mean, that was the original motivation for our study. Are these predictions borne out by experiments? And so you get a fluid-like stress, except for this normal stress difference, but that's a small matter. We won't worry about that right now, but otherwise fluid-like. So the only shear stress is the azimuthal shear stress. So that's what we set out to do. So until now, which is 25 minutes, I guess, is just introduction. I'm going to introduce to you the what I've already talked to people over here, and there's several people over here in the audience before about, namely the results of our experiments, and then tell you how we managed to resolve an anomaly we observed in the results. So what we're doing here is using this strain gauge sensor to measure the traction on the outer cylinder as a function of depth. Okay, so there's a slider that can move up and down, and this sensor is mounted on the slider, and the sensor can measure the shear as well as the normal forces acting on it. All right, so that's what essentially we've done. We can also image from the top using a video camera and measure the velocities in the free surface. Of course, you can't look deep into the material because it's opaque. And the materials that we normally use to study are glass beads. We've also used mustard seeds, but I'm not going to talk about mustard seeds today. So calibration was, as I said, I already explained to you that if you measure the stress as a function of depth, then it should saturate, right? That's what the simplest analysis tells you, and it indeed the experiments indicate that they indeed do. They saturate beyond a depth of about, so the depth is normalized by the Couette gap, okay, the distance between the inner and outer cylinders. So beyond a distance about 2 to 3 Couette gaps, the stresses saturate. Oh yeah, that's because you're getting close to the bottom wall, and there the flow is more complicated. So if you ignore these points, then this is static. Yeah. Oh, that's right. Yeah. So there's no flow, but the bottom wall does hold some stress, right? There's an impenetrable base. So the Janssen analysis holds for an infinite column. There is no base. So thank you. Yeah. So one should ignore these because you're getting too close to the base where the analysis doesn't hold. But the moment you start shearing, you see something completely different. So, first, these data points are for the static, which I already showed you. The blue line is what you would see if it were a fluid column. Okay, so that's the hydrostatic line. So, the static stresses are much lower than the hydrostatic stresses. They saturate. The moment you shear, the stresses, all the stress components seem to exponentially increase with distance from the free surface, okay, with depth. So, this is the normal stress, the radial normal stress. This is the azimuthal shear stress, sorry, the vertical shear stress. Okay, so that's the vertical stress exerted by the material on the wall. Okay, vertical traction by the material on the wall. And it's more or less independent of shear rate, as you would expect. There's very slight shear weakening, but that's also been observed in previous experiments. But it's largely independent of shear rate. So, these are clearly contrary to plasticity theories. Okay, plasticity theories would tell us that they should all go linearly in with the depth. So, essentially, this is where we made some conjectures. When I last spoke to you, to some of the audience over here, about what causes this anomalous stress when you start shearing this Couette column. Well, is it first, is it the impenetrable base? Yeah. No matter how you do this, whether you stop and start many times. Time scale on which. Oh, you're asking what is the time scale? Yeah, there is time scale. It's of the order of a strain of about 50. It takes a long time. Okay.
It still resembles the original tensor profile if you're not on that time scale. And then
so, for very short time, it doesn't resemble this, but the stresses are of this sign. So, in other words, for very short time, the walls are holding up the column, but after a strain of about 50, the shear stress switches. So, that's the other thing I wanted you to note over here. The reason the normal stress increases exponentially with depth is because the shear stress switches sign. So, initially it's holding up the column. After you shear it for a while, it pushes down the column. Okay, the wall is pushing down the column. So, it takes a strain of about 50 to do that.
does it depend on the depth?
No, does not depend on the fill of the column. No.
No, not in that.
Column fill.
The steady state is approached in sigma RR.
Okay, so if you measure it at different points, no, it doesn't. It largely does not. So, maybe I should have shown you that. This is what it's like. So, this is the vertical shear stress as a function of strain. Okay, strain is equivalent to time. So, initially it's it's positive, indicating that the walls are holding up the column, and after a strain of about between 20 and 50, these two are for two different kinds of walls, they switch. Okay. and it does not depend on the depth. Okay. So, what is the reason for this anomalous behavior? So, could it be the impenetrable frictional base? Well, if you do the experiment for two different column heights, the stress profiles essentially fall on each other. Okay, so clearly the column height has very little to do with this anomalous behavior, and we've done it for other column heights. Now, is it because the material is dilating? Now, it's well known that when you shear a granular material and you deform, it dilates. Grains try to move, when they try to move past each other, they have to move apart. That was discovered by Reynolds long ago, and is named after him, Reynolds dilation. So is it because of that? Well, it isn't, because we shear it for so long that dilations happened. We are at steady state. Okay, and secondly, after you fill the column, and we fill it by raining the glass beads down, and you start shearing, it actually drops. The column height drops. So it's not dilating; it's in fact compacting initially. And beyond a certain time, it remains constant. So it's fully dilated or whatever, compacted, but it's not changing with time. Yeah, right.
So the impenetrable part is important, and the friction part,
it would be flowing down.
Yeah, it would just go away, right? But even with the friction part, if you
so we've roughened it. That's right.
If you change the base and it's still the same, that's really very interesting.
We have a smooth aluminum or glass base, and we have a rough sandpaper coated base. It makes no difference. Yeah. So whether this experiment is done for rough Couette walls or base, glass beads or sand or mustard seeds, qualitatively everything is the same, right? Yeah. The particles. Yeah.
Particles of
it depends on the grade of sandpaper you use.
Right.
Okay. So the sandpaper we use are essentially particles glued onto it, and those particles are much finer than the beads that we're using. So if you measure for example, angle of repose on the sandpaper, it's much larger than it would be just the angle of friction of a heap.
Okay.
I mean angle of repose of a heap. Yeah. So the sandpaper does provide a lot, does increase the friction. Yeah.
Seems to be that it's like an initial value problem from the top surface in some way.
Yeah. Right.
So it's independent of the other side.
Yeah, independent of where the base is. Of course, we don't measure, as someone noticed, too close to the base, because then things go haywire. So then here comes the Taylor-Couette problem. Could this anomaly be because of Taylor-Couette vortices? So is there a secondary flow? Are the particles just spinning around, or are they doing something more complicated? Well, if it were like Taylor-Couette flow, which I showed you initially in the second slide, then imagine what the shear stress at the wall would have to do. It would be switching signs as you go from one roll to the next, right? If it were a fluid, and it would be the same for granular material if it obeyed those any of those plasticity theories. The shear stress would switch sign as you go from one roll to the next. So if you don't want the shear stress to switch sign, then you'd have to have one massive roll, right? And John Hinch is shaking his head, and that's what we did. We said it was impossible. How could you have one massive roll regardless of what the height of the fill is? And the roll had to be in this direction, in this sense. Okay, it had to be going up at the outer wall. Well, you see, the stress you measure is always such that the walls are pushing down the material, which means the material is pushing the wall up. So it has to be flowing up. The gradient at the wall has to be such that the shear stress, the traction on the wall is upwards. Okay, so that has to be the sense of the role then. So, and we decided that therefore it can't be any of those, it must have something to do with the fabric. And by fabric I mean the way grains interlock with each other and transmit forces, and this is an old idea which has gained a lot of currency, and it's almost accepted to be fundamental in the mechanics of granular materials, that there are these force chains that transmit forces, and the way the force chains are aligned determines how the stresses are transmitted. Okay, and these are images obtained by Bob Behringer's group, who used photoelastic discs. This is a 2D heap of photoelastic discs between two glass plates, and they use crossed polars to detect the birefringence in the discs when there is a stress applied. So the bright areas are the areas of high stress. So you can see that the stresses are more or less transmitted in columns radiating downwards from the top. So, and we thought, well, initially, if you can imagine the heap in the column, the granular column in the couette being such that the stresses are being transmitted downwards to the outward column. When you sheared it, then we thought maybe a column switched sign, a switched slope, and so the fabric changed, and we'd have to include the fabric in the description of the stress. Unlike in isotropic plasticity theories, the fabric finds no place because the material is assumed to be isotropic. Okay, and that's what our hypothesis was, and that I've spoken to Anurag Gupta about this. We were trying to formulate forms, simple forms, in which you could formulate a constitutive relation between the stress and the deformation rate and the so-called fabric tensor. Okay, so this is the introduction, 40 minutes of it. Next 20 minutes is what we've done since then. Now, to verify all this, we sought to do discrete element simulations, and essentially I won't go into the details of this. These are basically like molecular dynamic simulations, except that the potentials are like hard sphere potentials. Okay, particles don't interact with each other until they come into contact, and when they are in contact they interact as though they are a set of springs and dashpots. Okay, so for normal contact there is a spring and a dashpot. For tangential there is a spring and dashpot for tangential force, and importantly there is also a slider for tangential force. Okay, that provides Coulomb friction. So the tangential force cannot exceed a certain constant mu times the normal force. Okay, until that value until it comes to that value, the spring and dashpot determine the tangential force, but it can never exceed that constant times the normal force. So that's this model, and this has been highly successful, very used by a large number of groups very successfully to reproduce experimental observations in a variety of situations. So that's what we decided to do. Filled up this column with about 500,000 particles, and we used the simulation package called LAMPS, large array atomic molecular massively parallel systems, I think. That's what it stands for. Okay, the particles are almost, so this is highly exaggerated. So the maximum deformation is less than 1% of the radius. So this is just a schematic. Yeah. Steel shots or something like that. Okay, now, so basic validation. First is, what is the azimuthal velocity profile? The black dots that you see here are experimental observations now of Wolfgang Lozert and co-workers, and these are what you get from the simulations. So we observe a large amount of slip at the wall. Okay, so this is the inner cylinder, and that's the outer. Okay, you're going radially outwards from the inner to the outer over here, and that's the azimuthal velocity. So qualitatively, they are the same. You can see a roughly exponential decay of the velocity as you go from the inner to the outer cylinder. And these are in 3 different regions. So you were asking about whether the stress changes. What was it that changes as you go from the top to the bottom? So the time scale changes. So the velocity certainly doesn't once you shear it. So, and then second validation, what are the wall shear stresses? Well, they're so these are the wall stresses. These are normal stress, and these are the shear stresses. Now, so you have them both at the inner and outer cylinders. Okay, and at there should be opposite signs if you think about it. Okay, the inner and outer cylinders, if the walls are imposing a downward traction on the material, then the shear stress should be opposite signs, and they are. Okay, and the radial stresses should be of the same sign, and these are very similar to the experimental observations, right? So you know, these are the simulation cell was a column of 90 particle diameters. The experiments are of 900 particle diameters. So we can't reach that scale simply because the number of particles gets too large. But they have the same curvature. You can see that the normal stress is increasing more than linearly with distance. And the shear stress has the right sign. So, and then you ask, well, what else are they doing? And well, these particles are not just going round and round. The motion is not azimuthal. There is a vortex, a Taylor-Couette like vortex, and there is only one. And no matter what size of the column you choose, there is one large vortex. Okay, now this kind of explains the observation, right? Because there's one large vortex and the velocity is decreasing as you go to the outer cylinder, then the material is imposing an upward shear stress on the wall, and therefore the wall has to react by pushing the material down, and therefore you get all components of the stress blowing up. Okay, so yeah, go ahead.
You said your diameter is 900, the interpart.
Column height is 90 particle diameters.
How does the simulation?
Couette gap is 15 particle diameters.
And in your experiments?
We all in our experiment we've done 15, 40, 30,
Okay, so
several
in that
bits.
sense it's comparable.
It's comparable, yes. It's not the same, but it's comparable. Irrespective of the strain rate, irrespective of the column height, and irrespective of the Couette gap. Yeah, it doesn't matter. So yes, we have data for that too. We've done it for 3 different shear rates. You get, in all 3 cases, you get a single vortex. Yeah. Oh, okay. The Savage number is of the order of 10 to the minus 6. Yeah, it's very slow. The rotation rate is about 1 RPM. Yeah, Ganesh.
Depth of the Couette gap. The radial one.
1 over the depth. Well, I mean, it has to satisfy mass balance. That was your question, right? So, I mean, we are not losing particles. But you can see that it's not shearing all the way to the outer wall, and it's not, I mean, the velocity is not going all the way, the vortex is not going all the way down to the bottom wall.
So then eventually it should become independent with the depth. What you're
So
seems
you're
to be
asking, is the vortex size independent of depth?
That's what you said seemed to suggest.
I said there's one vortex.
No, just now that the velocity seemed to be dropping away.
As you go to the bottom,
Yeah.
It could be. So, you know, these are expensive calculations to do. Each of them takes about a week on a cluster of 128 cores, unlike somebody who had used 2,500 cores earlier this morning. Yeah, so I didn't have access to those. Yeah.
With the Couette gap depth.
Yeah. So all of them seem to decay very rapidly. So this is about 0.6 times the width of the gap, the Couette gap, I mean, which is about 10 particle diameters. Within about 10 particle diameters, you no longer see motion beyond. Okay, so these are just stationary particles. So there is a outer layer which is essentially static, and close to the, but you know, you can see over here that the very close to the inner cylinder, that's the inner cylinder, particles are rolling all the way down. So, but I mean, I see what you're saying. Mass balance has to be satisfied, and so it will be. So one can get the scaling, yes. Yeah. So it's not symmetrically placed between the pre-surface and the bottom, right? Yeah.
Did you put a few colored particles and then?
Yeah. So I was going to show you that. Yeah. So is this indeed true? Is this an artifact of our simulations? And that's what I was going to show you. Yeah. So we did some experiments after that to look at this. Actually, we were simultaneously doing this as well. So these are, can you see this video? So that's the Couette gap of approximately, I think, 18 particle diameters. Towards the inner cylinder, we've laid some black beads, and these are all white beads. And we're shining light from the top and taking images. And this is, by the way, played at 10 times the normal speed. Okay, just to, again, you can see a radial movement. You can see the black beads going down near the inner cylinder, right? They've disappeared now. And if you watch over here, they'll be popping out. You see one over there. There. Yeah. There are a few that will keep popping out. Unfortunately, we can't look deep in to see where it's going, to what depth it's going in. But there is a clear radial motion inward into the inner cylinder and down from the inner cylinder. They're both 0.8 millimeters. Yeah, the black ones have just died. Yeah. You know, we can't, we don't have great control over the size. Yeah. We've sieved it as much as we could. So this is a video of the simulation, the different colored particles. You can see clearly that, let me go back. So there are 3 bands of particles, okay, with different colors, and the idea is to show you what these bands do. So the topmost band is near the free surface. This is somewhere in the middle, and this is not all the way at the bottom, but somewhere close. and so very close to the inner cylinder, the particles just drop, and these slowly move up. So velocities out there are much lower, but the net flux everywhere is the same, 0. And so this is what a secondary velocity field looks like if you want radial and azimuthal velocity. So radial velocity is inward velocity of the particles is negative. Okay. Please ignore all the colors and just look at the green lines. And what do they mean? Okay, ignore the colors. The green lines are, this is at the free surface, and then as you go further in, it rapidly goes to 0, deep down. Okay, this is the free surface, and you're going deeper into the bed. The other red and blue lines are for different shear rates. So here again, the azimuthal velocity is a maximum downwards near the free surface, and as you go down, it decreases. Now, there's another little feature though. So, why would they be moving inwards towards the inner cylinder? So, this is a question Ganesh asked me, because if the surface is free, then the shear stress, the radial shear stress, radial shear stress of the free surface is 0. So, and the centrifugal forces are throwing the particles out if they are of significance. So, the particle should be able to move out at the free surface and should be moving in downwards, right, as you go down. Well, it so happens that the surface is tilted. So, that is the free surface profile. But as you keep shearing harder and harder at higher shear rates, it flattens out. Okay, so there is a difference. You keep shearing it when you go from 0.45 reciprocal seconds to 20, the surface sort of flattens out, but the vortex remains, and it's always of that sense. It begins flat when it's in a stationary column. As you keep shearing, it tilts. But then if you increase the shear rate, it flattens out again. I am almost there, near the end. But so all this seems to explain the anomalous stress, at least qualitatively. Okay, that there is the stress switches sign when you start shearing. So qualitatively, the shear stress at the outer wall, so vertical shear stress, switches sign because there is a roll, but it doesn't explain this. Okay, and this was something that an earlier student of mine had suppressed because he thought the data was wrong. It turns out there is a slow oscillation of the stress, and he had just averaged it over 2 or 3 cycles and given me the mean stress. But this is fascinating. The oscillation is exactly the same period as the rotation. Okay, because initially we thought the oscillation was because of a wobble of this inner cylinder, and we tightened all the bearings and measured the wobble. Okay, and the wobble got down to 40 microns. 40 microns is about 1/20th of a particle radius. Okay, and 1/1000th of the Couette gap. So it's really small. That's the wobble, but there is still an oscillation. They're not exactly in phase in this part, but they seem to be here. The wobble and the stress. Okay.
Do you see these oscillations in the molecular dynamics simulation number?
So we haven't done it for that long.
Yeah, because then your this premise of wobbling can be more clearly sort of rooted out, isn't it?
Wobbling can be completely eliminated.
Yeah.
Yes, right. Yeah. So that's what we are trying to do. Trying to do a long simulation, so which is going to take a month. So this is, I'm not saying this is due to the wobble. I'm just saying there is a small wobble. Yeah. So I'm measuring the radial normal stress at a particular point. Yeah, so very unlikely, but we can't do that because the slider is fixed at one particular point. We've done this experiment repeatedly by reining it again and again, and you measure the same thing. So it can't be a function of the angle, right? And that's why we're trying to introduce fabric into the constitutive relation to the stress. In the fabric, you can think of as just the way it's like fabric in a textile. The way the yarns are, orientation of the yarn, where it carries stress. So this is what the fabric looks like. We can access that in our simulations, right? Because we know the contact forces. We can propagate them along the chain, if there is a chain, and look at what the fabric is like. And these are all contact forces which are above a certain minimum. Okay, we have set a minimum bar. Minimum is about twice the average contact normal force. Okay, so all contacts that carry a force greater than twice the average are put in here. This is diagram. And you can see. Can you see any force chains? This is of course a 3 dimension, so it's hard to see. We tried it at various angles. We could not see any sign of change. Okay. If you project this, yeah.
Which is the cylinder which is hollow?
Oh, okay. So this is the outer. This is the outer cylinder. Inner cylinder is somewhere up there. It's just a section. I have some of the images if you like. I'll show you later. If I project this and just take the 2D snapshot looking from above, that's what it looks like. I don't see any change.
What about another view?
Another view? Yeah, I have lots of views. I don't have time. Yeah. I can show it to you later. No matter how you look at it, so what instead of chains, they simply clumps. So if you follow particles that carries a large force near the inner cylinder, it doesn't go very far out, it turns around and comes back. They don't seem to be changed. The forces disperse beyond a point. Okay, so they're not correlated. You need, you need a correlation in the direction of the force transmission in order to get a change. You don't get that. So I'll show you a quantification of that in my next slide. So this is, seems very, very different from what Bob Behringer has measured. This is a 2D couette. So he has the same photoelastic discs between two cylinders, but this is in 2 dimensions. And he sees force changes.
So what means it's a very, very thin thing.
Oh, it's 2D, so it's discs, like a monolayer of discs. Otherwise you can't see through them.
Prabhu, what is how do you estimate the friction between the inner wall and the particles, and how does that compare to the friction between the particles? Because there is a possibility, I'm just thinking about.
Simulations or in real life?
In any case, because if you're seeing this, well, you think you can control that pretty well in the simulation, right? So.
Yeah, the simulations they are parameterized.
Right, so they're
equal. The simulations are equal. And the wall, we roughen the wall for that very reason, to make the wall as rough as possible, almost as rough as particle. So, now to quantify this force change, you try to measure an order parameter. This would be the 2-particle order parameter. Okay, without removing the isotropic part. So if there are 2 particles in contact, particle 1 and particle 2, N12 is the contact normal. Okay, the outer product of N12 itself is the tensor, so that's the pneumatic order parameter, right? But you're not looking at 2 particles in contact, you're looking at many particles in contact. That forms a chain, right? And so this would be the extension of that for many particles in contact. So you just take the dot product of every pair that's in contact along the chain. That gives you rank 2 tensor order parameter for a chain. Okay, so that will give you an idea of whether the chain is pointing down or up. That was the idea of measuring this. So now if you take the find out the eigenvectors of this, that is get the principal directions and see how they are tilted and measure the tilt with respect to the horizontal. So this is the theta is the tilt. Okay, and these are the distributions of these of this order parameter. Okay, the primary eigenvector tilt with the horizontal. You can see that it's tilted slightly up on average. So the chains which initially in all experiments are pointing down seem to be pointing slightly up. Now whether it is significant or not, I don't know. Whether it's statistically significant, I don't know. But they do seem to be pointing slightly up.
What is this angle?
This is the angle of the principal eigenvector of this order parameter with the horizontal. It essentially gives you an idea of if there is a dominant direction in which the forces are transmitted along the chain, what would that be? What would the inclination be to the horizontal? Okay, so to conclude, well, there is a Taylor-Couette like secondary flow. Is it in the classical Taylor-Couette flow? It is caused by it's a centrifugal instability. So the centrifugal force is throwing the liquid out, and until the critical Taylor number, the pressure difference is holding back the fluid. But beyond a certain point, the pressure gradient can no longer hold the fluid, and the fluid sort of forms vortices. So, is it a centrifugal instability? Well, that's what we're trying to find out. Do a small perturbation analysis like John Lynch did, but a small perturbation analysis of the plasticity equations to see if we can recover these kinds of secondary flows. That's work in progress. But it is, even if that did explain the secondary flow, it doesn't explain this. Okay? So, in our experiments, if we vary the Couette width, classical analysis should tell us that all these curves should fall on the same line. Because we are scaling the depth by the gap, and the gap is the relevant length scale. Okay, stress is scaled by rho g times the gap, and the vertical distance is scaled by the gap. They should all fall on the straight line. They don't. Okay. So it doesn't explain everything. And that is if you believe plasticity here. So, and as I said, we're trying to do a perturbation analysis of the plasticity theory for the small centrifugal force. And finally, the last few slides that I showed indicate that maybe the stress chains are an artifact of 2 dimensions. Perhaps they do not exist in real 3-dimensional situations. So, still to be verified. More experiments.